This is a solution guide for the second multiple choice section of the Calculus AB AP exam. You have 15 minutes to complete 17 questions. The best way to study for these exams is to do as many problems as you can. So this is to help you prepare. I have a link down below with a blank complete AP exam, and here's a solution to section 1, part B. Let's get started. So for the first problem, we're given the graph of the function f shown in the figure above, and we're asked to find which of the following values of x is f prime of x positive and increasing. So the first thing to notice is that they've given us a graph of f, but they're asking us to find positive and increasing values of f prime. So f prime is the slope. So now just looking at each of the values they've given to us, let's just draw what that slope looks like, right? So at point A, it's that tangent line. At point B, well, there is no tangent to this line, so there is no slope. At point C, something like this. Point D, it's something like that. And point E, it's something like this. Okay, so those are the slopes. And now we have to find at which value are the slopes positive and increasing. So for A, if we look at the slope here, this is a negative slope. It's pointing down. So it cannot be A. At point B, we have no slope because it's not differentiable at that point. So the answer is not B. At point C, it is increasing because it's a upward slope. So it's a positive slope, but the slope itself is not increasing. And what we mean by that is that as you move from left to right, you can see that this slope becomes less and less positive. So at the next value here, you can see it flattens out. That isn't as positive as the previous value, so it's not increasing. The answer is not C. If we look at point D, this is a negative slope. And then we have E. It's a positive slope, and as we move from left to right, the slope gets steeper and steeper, which means it's increasing. So the answer here is E. The next problem, let f be a function that is continuous on the closed interval 2 to 4 with f of 2 equal to 10 and f of 4 equal to 20. Which of the following is guaranteed by the intermediate value theorem? So the intermediate value theorem tells us that between our interval of 2 to 4, we know for certain that there exists values on these intervals that are between the two y values. And the reason that's true is because we know that the function is continuous between our 2 points, which means that there exists some line that goes between these 2 points. And that tells us that for each of our values between 2 and 4, there does exist a value between 10 and 20. Okay. Now, let's go through each of the statements and see which one is guaranteed. So not just sometimes true, but always true. The first one says, A says, f of x is equal to 13 has at least one solution in the open interval 2 to 4. So this is true. Based off of the intermediate value theorem, we know this to be true. Let's just check out some of the other possibilities and see, if we may have gotten this wrong. B, f of 3 is equal to 15. So we can't say this for sure. Like f of 2.5 might be 15 or 4 might be 15, but we can't say for certain that any specific value is exactly 15. Then we have f for C. F attains a maximum on the interval 2 to 4. So this we also cannot say for certain. There's nothing that's been given to us here that tells us about maximum or minima, so we can't say C is always true. D, f prime of x is equal to 5 has at least one solution in the open interval 2 to 4. So we should be careful. So now they're talking about the derivative of f. So they're saying that on this interval, there is some point that has a slope equal to 5. Well, we also can't say this to be true because it could be 4.9 or 5.1 or any value in between. It doesn't have to be equal to exactly 5. Nothing about the intermediate value theorem specifies the slope. So it's also not D. And here we also have that f prime of x is greater than 0 for all x in the open interval 2 to 4. And we also cannot say this is true because let's just say that the line between these 2 points was something like this. So you could see here that for this portion of the line, our slope could be negative, which would not satisfy the statement. So it's not E. And the answer here has to be A. 78, the graph of y equals e to the tangent of x minus 2 crosses the x-axis at one point in the interval 0 to 1. What is the slope of the graph at this point? So whenever you see like a function looking for, like a x-axis or a 0 on some interval, you want to think, use my graphing calculator, graph this out, find some zeros, use the calculator function on your calculator. And this question asks us to find the slope of the graph at the point where it crosses the x-axis. So what we need to do is go into our calculator, enter in the equation y equals e to the tangent of x minus 2. And then for the interval from 0 to 1, we want to find the 0. So find the point where this line crosses the x-axis. And if you plot this out, you will find that x is equal to 0.606 with some trailing values. You could save that as a variable when you calculate it, or you could just truncate it and just realize that you've truncated the value of that 0. So the next thing is, once we get this x value, we need to find the slope of the graph at that point. So to find the slope, we need to find the derivative. So we're given y, so we need to find y prime. And for this, we need to remember our trig functions, so the derivative of trig functions. And we also need to use the chain rule because we have e to the power. So this will become the derivative d dx of tangent of x times e to the tangent of x. And then this just happens to be secant squared x e to the tan x, and we just have to plug in our value of 0.606 into this equation, and when we do that, we'll get the value of 2.961, which matches up with D. So the answer here is D. 79. A particle moves along the x-axis. The velocity of the particle at time t is given by v of t, and the acceleration of the particle at time t is given by a of t. Which of the following gives the average velocity of the particle from time t equals 0 to time t equals 8? So when we're asked to find average velocity, we know that we're going to be dividing by the period that we're taking the average over, which is 8 minus 0. So we're going to be looking for something that's 1 over 8 to find our average. And anything that doesn't look like that is probably not right. And the next thing we need to do when we're finding average velocity is we need to calculate the total amount of velocity over that period and then divide it by that window, and that gives us the average. So this one, we're going to find, to calculate the total velocity over that period, will be the integral from 0 to 8 of our velocity equation. So v of t dt. And then we divide this by 8, right? So this now gives us the sum of our velocities between 0 and 8. And then we divide it by that window, which now gives us the average. It's another way to write this. It's 1 over 8 of the integral from 0 to 8 v of t dt. And this matches up with B. All right, now, but just looking at some of these other answers, we can also, if we didn't solve for this, we can also intuit our way to the right answer. If we look at A, this gives us the acceleration at t equals 8 minus the acceleration of t equals 0 divided by 8. So this gives us the average value of these two accelerations, which is not what they were asking, so it can't be A. And if we look at C, we're taking the absolute value of the velocity. So this is equal to the speed. So this integral gives us the average speed of the particle. All right, so I should scratch all that. Scratch that, scratch correct, scratch correct, scratch correct. Okay. All right, question 80. The graph of f prime, shown above, the derivative of the function f, which of the following statements must be true? Okay, so they're given three statements. The first one says f has a relative minimum at x equals -3. So it's talking about f, which is the integral of our function f prime. Okay. Statement 2 says the graph of f has a point of inflection at x equals -2. And the third statement is the graph of f is concave down for the interval of x greater than 0 and less than 4. All right. So one thing we can do here is now just identify some of the things that they're asking us to find. So relative minimum occur at points where the derivative of f are 0, right? So if we had some plot of f that looks something like this, the minimum or maxima occur when the slope is equal to 0. And so this is f. That means that these 2 points occur when f prime is equal to 0. So now looking at our graph of f prime, we see 2 zeros here and here. So the only possible places for any sort of minima, or any sort of like minima or maxima, are at x equals -3 and x equals 2. Okay, but now we found that there's a 0 here, so we know it's some sort of minima or maxima. But to figure out if it's the minima or a maxima, we now inspect the slope around those values. So what we mean by that is, if we know that we have a slope of 0 at some point, if the slope before it is negative and the slope after it is positive, then we know that's a minimum. And likewise, so if the slope before it is positive and the slope after it is negative, then we know it's a maximum. So for our point here, x equals -3, the slope before it, or negative, it's negative. These are all negative values. And the slope after is positive. So this tells us that this is a minima. And therefore, statement 1 here must be true. Okay. Now for statement 2, the graph of f has a point of inflection at x equals -2. So if you remember from your math class, points of inflection occur when f double prime of x are equal to 0. So looking at our graph of f prime, the points where the f double prime of x are equal to 0 is when the slope of this graph is 0. So the only point that really stands out here is this one. This, like here, it looks like it might equal 0, but it's not. It doesn't change. Like the direction doesn't change. So this is actually not a point of inflection. Oops. So that tells us that this point here, x equals 0, is the only point of inflection, and point 2 cannot be true. So there is not a point of inflection at x equals -2. Right? This is tempting, but it's not a point of inflection because it does not. The slope doesn't actually hit 0 and come down. Yeah. Okay. And 3, the graph of f is concave down on the interval of 0 to x to 4. So they're saying that between this point and this point, the graph of f is concave down. Now, we do know that there's a point of inflection here. Right? So this tells us that the period after this, before this, it changes from concave up to concave down. And and we know that we have a minima or a maxima here at x equals 2. And so because the slope before x equals 2 is positive and the slope after is negative, we know it looks something like this. Right, so this is x equals 2. Before it, the slope is positive. After it, the slope is negative. So this is a concave down. And that is true. It satisfies statement 3. So we know that 1 and 3 are true. And the answer here is E. 81. Water is pumped into a tank at a rate of R of t is equal to 30 times 1 minus e to the negative 0.16 t gallons per minute, where t is the number of minutes since the pump was turned on. If the tank contained 800 gallons of water when the pump was turned on, how much water to the nearest gallon is in the tank after 20 minutes? So this one is a simple integral. We just need to sum up the gallons that are accumulated using this rate equation, and we're also given a starting value of 800. So the equation would be something like 800 plus the integral from 0 to 20 of r of t dt. And this one you definitely would want to use your calculator, and when you solve it out, you would get the answer D, 1,220 gallons. 82. If f prime of x is equal to the square root of x to the fourth plus 1 plus x cubed minus 3x, then f has a local maximum at x equals. So again, if we want to find maximums or minimums, we're looking for points where the derivative of that graph, so f prime, is equal to 0. So all we need to do is plot on our calculators the equation of f prime of x that they've given to us, and it sort of looks something like this. And we need to find all of these. We need to find all the values for these zeros. And once you've found these zeros, now we need to figure out which one is a local maximum. And similar to the problem before, maximums occur when the slope, so this is a maximum. Maximums occur when the slope up to the peak is positive, and then the slope after it is negative. And if you look at the graph that you plotted on your calculator, this is the point that we care about, because the slope before it is positive and the slope after it is negative, which means that this is a maxima. So the answer here happens to be this point, which is 0.350, which is C. 83. The graph above gives the velocity v in feet per second of a car for t greater than or equal to 0 and less than or equal to 8, where t is the time in seconds. Of the following, which is the best estimate of the distance traveled by the car from t equals 0 until the car comes to a complete stop? So we need to find the total distance traveled using this velocity versus time graph. You may understand that that's essentially just the volume under this curve. It's the velocity times the time. So there's a few ways you can solve it, but there's one that makes it really simpler. And that's just to realize that this graph is almost like a straight line. So if we were to draw a straight line between t equals 0 and t equals 8, this area above is almost equal to, but a little bit greater than that area below. So if we use this approximation, the area under this curve is now just the area of that triangle. So it'll be the base 1/2, the base 1/2, the base times the height. The base is 8, the height is 50. So this is approximately 200. And we note that the area that we lopped off from up here is a little bit greater than this area down below. So we know it's almost 200 and a little bit greater than 200. And just looking at our options here, that gives us D. So our answer is D. Now, a more accurate way of solving this problem, if it wasn't easy to make that into a triangle, would be to calculate Riemann sums. And then you can either pick left or right or middle Riemann sums based off what you're given. And then you would get an answer, which would either be an over approximation or a under approximation, and then you could pick which is the best answer. But in this one, there's a shortcut. You just make it a triangle, and the answer is D. 84. For x greater than negative 1.5 and less than 1.5, let f be a function with first derivative given by f prime of x is equal to e to the x to the fourth minus 2x squared plus 1 minus 2, which of the following are all intervals on which the graph of f is concave down. So to find the points where this is concave down, we want to use a calculator and find our points of inflection. So we have this interval from negative 1.5 to 1.5. And concavity changes wherever we have, so concavity changes from concave down to concave up whenever we have a point of inflection. And points of inflection are when the second derivative of our function f is equal to 0. So since we've been given this first derivative, which is f prime of x, all we need to do is find the points where f double prime of x are equal to 0. And the first step is just to plot out the equation they've given to us, which is f prime. And if you do that between the interval of negative 1.5 to 1.5, you see that it looks something like that. That's a terrible drawing, but it's something like that. And the points where we have the points of inflection here are where the slope is equal to 0. That's when f double prime is equal to 0. So we have points of inflection here, here, and here, which means that concavity changes directions here, here, and here. So from this, now to find which way, like which points are concave down, we need to see where the slope goes. Let me write this down. Concave down. Concave down occurs when the slope goes from positive to negative. And if you remember why that's true, it's because a concave down, a portion that's concave down has a maximum, which means the slope in front of that point is positive and the slope after it is negative. So if we look at our intervals, for this first interval, the slope here is negative. So this is not concave down. There's no positive slope. (84) For x less than 1.5 and greater than negative 1.5, let f be a function with first derivative given by f prime of x is equal to that equation, which the following are all the intervals on which the graph of f is concave down. So we're looking for concavity for graph of f. We're given an equation for f prime, and we have a few solutions, a few answers that we can choose from. There are different regions in which concavity is likely concave down. So what we need to do here is find two things. It's points where concavity changes. So where does concavity change? And then what are our critical points? And the reason we care about these, where concavity changes is the end of a boundary. So if we're looking for these boundaries where it's concave down, well, we need to know when it starts and where it ends. So that occurs when concavity changes. And we know that concavity changes at inflection points, which is when the second derivative of f is equal to 0. And we care about critical points because the critical points are minima or maxima. So they make up those peaks and the bases of a concave down and a concave up portion of the graph. And we know that critical points, right, that occur at the peaks or maximum, and these occur when the first derivative of f is equal to 0. So to inspect our graph of f, we're given an equation of f prime. So let's just graph that. Pull out your calculators, enter in that equation for f prime, and plot it out. And we're given an interval of negative 1.5 to 1.5. So set your window to be that. Now, when you plot this out and you play around with the y max and y min, you'll get something that sort of looks like, let's see if I can draw it. Yeah, something like that. And here we can see that this is a graph of f prime. Okay, so now our critical points occur, say, here, 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 right? So it's wherever f prime of x is equal to 0. So these are the points where we have minima or maxima. And our inflection points are where the slope of this graph are 0, which occurs here, here, or here. Let me use a different color. So our inflection points are here, here, and here. So this tells us that we now have 3 boundaries. We'll call this the first one, second one, third one, fourth one. There's 4 boundaries where we have some sort of concavity, and it's going to change at each of those intervals. Now, a key aspect of something that's concave down is that before our critical point, the slope is positive because it needs to go up to that max, and then after it, it's negative, which means it's decreasing. So the signs of a concave down portion are increasing slope up to, starting from the point of inflection, increasing slope up to the critical point, and then decreasing slope after that. So looking at our intervals here, starting all the way from the left, we have positive slope. So you don't want to get confused. Well, it seems like this is decreasing, but we're looking at f prime of x, which gives us the slope of our graph of f. So all these are positive slopes up to our critical point, and then after the critical point, they're all negative. So this whole region is concave down. The next interval we have negative slope up to the critical point followed by positive, so that's actually concave up, so we don't care about that. Then we have a point of inflection, then we have positive slope up to the critical point, and then negative slope after it. So this region is also concave down. And then you can see for yourself that last region is concave up. So we have 2 regions which look like they're from negative 1.5 to some point in between, probably around 1, and then from 0 to 1, which just happens to be D. That's the answer. Question 85. The graph of f prime, this is the derivative of f, is shown in the figure above. The function of f has local maximum at x equals. So we need to find where there's a maximum point. Remember, maximums, local minimums, extreme maximums, and so on, they occur when the derivative of f is equal to 0. And you'll notice that on our graph of f here, there are 2 points where it's equal to 0. So those are potential minima or maxima. And let's see. So those match up with any of our options. This is x equals -3 and x equals 1. Yep. So here we can tell that it's either A or C. And the points around it tell us whether it's a maxima or minima. So for example, for -3, we have negative values of slope before it, followed by positive values. So that's something like negative followed by positive. So this happens to be a minima. For 1, we have positive values followed by negative values. So it looks something like this, which is a maximum. So the answer here is C. The maximum occurs at x equals 1. 86. If f prime of x is greater than 0 for all real numbers x, and the integral from 4 to 7 of f of t dt is equal to 0, which of the following could be a table of values for the function f? So now we have 5 options, A, B, C, D, and E. I'm going to slide up and slide down. You can't see all of them all at once. But these tables give us values for x from 4 to 7 with their y values at that point. And we need to find ones where the integral from 4 to 7 comes out to be 0. So what's actually being asked of us, if we just draw a sample plot, we don't actually know what f of t is besides some of the values that are given to us. Let's just assume it looked like something like this. right? It's saying that the area under the curve of these points sums to 0. So it's equal to 0. And we also know, if we look here, that f prime of x is greater than 0. So that means that it's a positive slope for all the values. So I'm actually going to take back what I drew and draw something that looks like this, right? So positive slope, meaning that the values of f are increasing, and the area under the curve sums up to 0, right? So now, just thinking about this, if our line, our function f was always positive, well then this area under the curve would be positive. And likewise, if the line was always negative, well then that area under the curve would always be negative. So in order for the area under this curve to equal 0, there needs to be some negative values and some positive values for it to cancel out. So now looking at our options, we look at A. So now looking at our options, for option A, we're given a negative value for f of 4, a negative value for f of 5, and then f of 7 is 0. Now we know here that all these values are less than 0, and even though they haven't given us 6, we know that 6 has to be between, or f of 6 rather, f of 6 has to be greater than negative 3 and less than 0. That's guaranteed by f prime of x being greater than 0. So all of the values in this table are negative, so that area under the curve can never be 0. It's going to be some negative number, so it's not A. If we go to B, we have some negative 4 for 4, negative 2 for 5, and then a positive value for f of 7. So this one, it's actually plausible. These numbers are increasing. So negative 2 is greater than negative 4, 5 is greater than negative 2, and they're positive and negative values. So B could be the answer. If we look at C, we have f is equal to negative 4, 5 is 6, and 7. F of 7 is equal to 3. Now, this one might be tempting. You might be tempted to say this is possible, but if you remember that f prime of x is greater than 0 for this whole period, and that tells us that the values must increase. But here, from f of 5 to f of 7, the value did not increase, so this is not a possible table. In D, all the values are the same, so this means that the slope would just be 0, so f prime of x is not increasing. It can't be this table. And then we come down to E, and you notice that all of the values of f of x are positive. They're greater than 0, so there's no way that the area under this curve could be equal to 0. It will be a positive value. So the answer here is B. '87. The graph of f double prime, the second derivative of f, is shown above for the interval of x greater than or equal to negative 2 and less than or equal to 4. What are all intervals on which the graph of the function f is concave down? So we're given the graph of f double prime. So our first step is to find the points of inflection to see where concavity changes. Our points of inflection are wherever the second derivative of f are equal to 0. And since this is a graph of f double prime, we have 3 points of inflection, which tells us that there are 3 regions of concavity. So before negative 1, between negative 1 and 1, between 1 and 3, and then after 3. So we need to find where all f is concave down. And it just so happens that when between those points of inflection, when f double prime of x is greater than 0, we know that it is concave up, and when f double prime of x is less than 0, it is concave down. Oops, if I could write that concave down. So we have here that, let's go something bigger. These two regions, f double prime is negative, and it's between our points of inflection. So these are the regions where it is concave down. And if we look at the options, this lines up with E. And that's the answer. Okay. 88. A person whose height is 6 feet is walking away from the base of a street light along a straight path at a rate of 4 feet per second. If the height of the street light is 15 feet, what is the rate at which the person's shadow is lengthening? So this is a classic related rates problem. We know that because we're given some rates, we're given some relationship, and then rates are changing. We're asked to find what is this other rate. And one thing I like to do for these is just start to draw out some of the values that are given to us onto the figure. So we have the height of this street light, which is 15 feet. And then we have the rate at which this person is walking, which is 4 feet per second. So I'm going to say that's dp for person. dp dt is equal to 4. That's a positive 4 feet per second. And we also have the person's height here, which is 6 feet. Okay. So the value that we're looking for is the rate at which the person's shadow is lengthening. And that shadow is this value here. It's like that triangle, right? Yeah. So, do we know anything else? Yeah, that's all we're given. So now when you have these related rates problems, you've probably seen a few of them, but when we're working with triangles, there's really only two types of related rates. One is similar right triangles, and the other one is to use the Pythagorean theorem. So in this case, you'll notice we're given two separate heights. So our intuition should be this might be a similar right triangle problem. So now under that similar right triangle problem, we're going to have two triangles and then some ratio which is fixed, and then some other ratio which is changing. And the fixed ratio is the height. So the height of the light pole here is 15, and the height of the person is 6. Those never change. But what is changing is this total length of the base. Because as this person walks further and further away, you'll notice that the shadow might grow and this base will grow. So those are changing. What helps now is to write this base in terms of the quantities we know. So we're going to call it, let's see. Let's change this color. This distance from the pole to the person, P. So that distance is P. And the reason I chose P is because I know I've already written down the rate at which the person walks is dp dt. So whatever the person's distance is from the pole at time t equals 0, for every time step after that, we know that it's increasing by 4 feet per second. So dp dt increases by 4 feet per second. And now the other quantity we're looking for here is the shadow. So I'm going to do that in green. And I'm going to call this S. Right? So the distance from where the person is to the end of this triangle is S. And the rate at which that changes is ds dt. And we don't know what that is, and that's what we're solving for. All right. So now we have our two triangles. You can see it. And the related rate is the height. So it's 15 over the base, which the base for the 15 triangle is where the person is plus the length of the shadow, P plus S. And this is equal to the height of the person, which is 6, over that shadow, which is S. And if I just multiply this across, I get 15S is equal to 6P plus 6S, which simplifies a little bit. We get 9S is equal to 6P. S is equal to 6 over 9P. And so that gives us a relationship. And now if we use implicit differentiation, we get that ds dt is equal to 6 over 9 dp dt. And you'll notice we're already given dp dt, which is 4. So if we plug in 4 for this dp dt, we see it's 6 over 9, which is 2/3 of 4, which happens to be 2.667. And so there it is. The answer for the rate at which the person's shadow is lengthening is B, 2.667 feet per second. Right. 89. A particle moves along a line so that its acceleration for t greater than or equal to 0 is given by a of t is equal to that equation. If the particle's velocity at t equals 0 is 5, what is the velocity of the particle at t equals 3? So the starting velocity is 5, and then there's some change of velocity. This is at t equals 0. And there's some change when t is equal to 3. So now this change is just the integral of our acceleration. Because the integral of our acceleration is acceleration times time for all the points in that period. So it's the integral from 0 to 3 of a of t dt. So this quantity here gives us the change in velocity. So if we want to find the actual velocity at t equals 3, we take the starting velocity, which is 5, and we add it to the change, and then that would give us an answer. So you can go ahead and plug that into your calculator, and if you do that, you'll find that the total velocity comes out to be 11.710, which is E. So the answer here is E. Okay. 90. Let f be a function such that the integral from 6 to 12 of f of 2x dx is equal to 10. Which of the following must be true? So this function, you'll notice, is in terms of x and dx, and all of the answers are in terms of t. So we know that we need to do a change of base, or a substitution here, to go from dx to dt. So you might be tempted to just say, okay, t is equal to 2x. So this whole integral is the integral from 6 to 12 f of t dt. And you might also say, well, okay, if I'm putting in t for 2x, then that means that my integral now goes from, if you plugged in 6 here, that'd be 12, and 12 there would be 24. So you might say, oh, it's actually the integral from 12 to 24 f of t dt. And you might be tempted to say that's still equal to 10. Now, this is actually incorrect. And the reason why is you cannot just simply plug in an equation and change what you're differentiating with respect, or what you're integrating with respect to. And the best way to think about that is when we do u substitutions. So if we did a u substitution with this, which this happens to be very similar to, you don't just change your dx to du. You actually need to solve for like some function where you get du in terms of dx, and then you plug that in. So we're going to do the same thing here to get the right answer. And we know that we're saying that 2x is equal to t. That's how we go from here to here. And now if we write x in terms of t, we get x is equal to 1 over 2t. So now dx dt is equal to, or like this, dx is equal to 1 over 2 dt. And now we can plug this in. So the integral, when we change the bounds, so 6, when we plug 6 in for 2x, that's 12. So we get from 12 to 24 of f of, again, we can plug in this t for 2x now. So f of t. And here we plug in this value for dx. So it's 1 over 2 dt is equal to 10. And if we factor out this 1/2 and then multiply it by 2 to both sides, we get that the integral from 12 to 24 of f of t dt is equal to 20. And that just happens to be B. So just be really careful on these problems when you see a change like you're substituting a function, you need to think a u substitution. You can't just directly go in and replace the 2x with t and change these boundaries and then change dx to a dt. That's not right. You need to actually solve for dt in terms of dx and then plug that back in. And that's how you'll get the right answer. 91. Let f be a polynomial function with value of f prime of x at selected values of x given in the table above. Which of the following must be true for negative 2 less than x, which is less than 6? So the options are the graph of f is concave up, the graph of f has at least 2 points of inflection, f is increasing, f has no critical points, and f has at least 2 relative extrema. Since we're given a table, you don't have a function that you can just put in a calculator and plot. So we're going to have to plot this out by hand. And that's definitely where you should start. We need to visualize what this graph actually looks like, or what this function actually looks like. So we have x equals negative 2, 0, 3, 5, and 6. At negative 2, f prime is 3, so it's some positive value. At 0, it is 1. At 3, it's 4, so it's higher than this last value. At 5, it's 7, which is even higher. And at 6, it's back down to 5, so something higher than f of 3, but less than f of 5. So if I drew a line, now notice this is just an approximation. The line can be anything in between, but we see it does something like this. And just be careful to know that this line could go it could go something crazy different, but it has to touch these points. That's what we know. And the general shape is still true, right? Yeah, to get to this point from here, the line has to decrease. And then to get this point to here, at some point it has to increase, and so on. So now, using that plot that we just drew up by hand, let's evaluate our options. So we have the graph of f is concave up. So now, is this always true? Well, if you remember, concavity changes wherever there's an inflection point. So even before we talk about concave up, for this region to have the same concavity throughout, it cannot have an inflection point, because if there's an inflection point, the concavity changes. So, and we know that inflection points happen when f double prime of x is equal to 0. And just looking at this chart here, I know that these you can't say that this is the exact plot, but you do see that the direction of this line changes. It changes twice, so from going down to going up, and then from going up to going down. And whenever it changes, the slope at some point is going to have to be 0, which means that there is an inflection point. So this plot has 2 inflection points. I can't say exactly where they are, but they exist in this period, which means concavity changes twice, and that means that the concavity can't always be up. Now going on to B, the graph of f has at least 2 inflection points. Well, this is true. We just spoke about that. Looking on this interval, we have regions where the slope changes its direction. So we know that somewhere in these 2 periods there are points where the slope is equal to 0, and that happens twice. So those are points of inflection, and there's at least 2 of them. So B is definitely true. C, f is increasing. Well, this is also not guaranteed to be true, because like I mentioned, this graph could look something like this, where and that means that in this region we have negative slope, so it's not increasing. So we can't say for certain that f is increasing. F has no critical points. Well, for that same reason I just described, we can't say it has no critical points. The critical points are when this graph crosses 0. So it's when f prime is equal to 0. So in theory, if it did look like something like this, well, we would have these 2 critical points. So we can't say for certain that f has no critical points. And f has at least 2 relative extrema. So now these relative extrema, again, occur when f prime of x are equal to 0. When the slope of the graph of f is 0, it means it's either a minima or a maxima. But to say that there are at least 2, it means that there are guaranteed to be 2 points on this graph where is equal to 0. So now we can't say that with certainty. Like there's a possibility it does. If the graph looks something like this, well, yeah, then we have these 2 points. that just means there's two critical points. But then to say that they're, yeah, but if the graph doesn't have to look like that, it actually doesn't have to cross the x-axis, in which case there'd be no critical points and no extrema. So it cannot be E, and the answer here is B. 92. Let R be the region in the first quadrant bounded below by the graph of y is equal to x squared and above by the graph of y is equal to the square root of x. R is the base of a solid whose cross sections perpendicular to the x-axis are squares. What is the volume of the solid? Okay, so this one's kind of wordy. We're given two equations, and they're told that there's a region R where this base of the solid is the cross sections perpendicular to the x-axis. So a lot of stuff, but let's just draw it out and then take it step by step. So we know that we're only dealing with the first quadrant, and we have one equation which is y is equal to x squared. So if I go, let's say this is 1, this is 1, y equal to x squared looks something like this, right? So x is equal to 1, y is equal to 1. Less than that, it's less than the straight line. And for our other equation, y is equal to the square root of x. Well, this one looks something like this. The square root of 1 is still 1, but values above it are slightly bigger. Yeah. All right. And if you're uncertain of this, just plot it on your calculator and you'll see it's true. So this region R is in the first quadrant, and it's below our graph of y equals x squared and above the graph of y equal to x. Okay, so we're telling us that R is the region in the first quadrant bounded below by the graph of y equals x squared and the graph of y equals x. So they're saying that it's the region in between these two lines, which is all of this. Okay, so this is R. And it's saying that R is the base of a solid whose cross sections perpendicular to the x-axis. So perpendicular to the x-axis is like this, right? So whose cross sections perpendicular to the x-axis are squares. So each one of these lines, if I was to draw it like that, makes up the length of a square. And it says, what is the volume of this solid? So what that solid is these heights. Each of those heights, if I pull this out, is the length of a square. So that length squared is the area, and the sum of all those areas is the volume, right? So I go this one, it's slightly bigger. Yeah. And so if I calculate all of those squares, the area of all those squares, and sum those together, that's going to give me the volume of this solid. So we know we're going to need to do an integral here, and our integral is going to go from the points in the first quadrant where they're contained, which just happens to be x equals 1. And you know that because if you set these two equations equal to each other, that's the point at which they meet. You can see that either just by seeing that like at y, like x for 1 for x squared, which is still 1, and the square root of 1 is still 1, so it's equal, or you can plot it and see that that's true. But our integral is going to go from 0 to 1, and it's from the area underneath this top curve, which is equal to the square root of x, to the area underneath, which is equal to x squared. Right? So it'll be the square root of x minus x squared, right? That gives us the difference. And now if you remember, we're integrating over the area of these squares. And the area of a square is the side length times the side length, which is the side squared. So we're integrating over this difference between those two lines squared, right? So now this in blue gives us the area, and the integral of that area gives us the volume, right? And we're differentiating with respect to x, which is dx. Okay. So now to actually integrate this, well, you can plug this into your calculator, see the bounds, and you'll get your answer. I'm just going to do it out by hand. And when solving this out by hand, it makes it easier to distribute, like to actually break this down a little bit. So what we would get is the integral from 0 to 1 of the square root of x squared, which is x, minus 2ab, that's minus 2 times square root of x times x squared, which is x to the 2.5, then plus x to the 4th dx. And then if we integrate this, we get x squared over 2 minus, 2 to the 1/2 is the same as 5 halves. So this becomes minus 4 over 7 x to the 7 halves plus 1 over 5 x to the 5th, all from 0 to 1. So this is equal to 1/2 minus 4 over 7 plus 1 over 5. Common denominator is 70. We have 35 over 70 minus 40 over 70 plus 14 over 70 is equal to 49 minus 40 over 70, which is equal to 9 over 70. And if you plug that into the calculator, you'll see this is equal to 0.129, which is A. So the answer here is A. And that's it. That's the end of this calculator section. Hopefully that wasn't too bad. You definitely want to use your calculator as much as you can for this section to get through these problems as quickly as possible. And you really want to make sure you're paying attention to when they're asking you about f versus f prime or f double prime. They like to confuse you when you take this exam. And again, my recommendation to prepare is to do as many problems as you can. I'll keep posting sample problems with links to those problems, and then I will post videos with the solutions. So if you enjoyed this video, you want me to keep creating them, please subscribe to my channel or like the video or leave a comment below.